Hello everyone and welcome back to Nunley Math. I'm your host Aaron Nunley. Thank you so much for joining me here today as we continue our discussion of graphs of functions. In the last video we talked about the linear function and some patterns that emerged when we were graphing linear functions. Today we're going to talk about a new type of function. I am not going to give you its name yet because we are going to talk about that together in just a moment. Instead, what I'm going to do is remind you that the job of the function is to take input values and match them to corresponding output values. In other words, for today, we're going to take values of x, plug them into our rule, and our rule's job is to match those to a y or f of x value. And then we're going to list those as coordinates and plot those coordinates on the graph. The goal today is to learn a little bit about this type of function. So we're going to do this the longest, most drawn out way possible, which means we're going to be picking values of x, plugging them into our rule. This says our rule is take x, square it, and subtract 5. So when I plug in a 0, I square it and I subtract 5. And we're going to get coordinates, and we're going to plot those one at a time on our graph. Now, the idea being that this requires very little understanding of this function because all we're doing is plugging in values and then graphing them as they appear. There are a lot faster ways that we can do this once we have a better understanding of this function, but it's a lot more beneficial for us, I think, if we discover those shortcuts together. So what I'm going to recommend that you do is that you pause the video, that you create your own table, that you create your own graph, and that you restart the video to see if what you get matches mine. It's a lot less effective if you just copy down what I read off to you. Because we did this in the previous video, I am going to plot these points a little faster, assuming that if you need more time, you're going to just pause the video to do that. And I'm going to start picking values that I know will appear on this x-axis. I don't want to pick values that are way out here or values that are way out here or that are hard to compute because it's just going to make it more difficult for us, even though there are values out there that might work. 0 I started with because 0 is usually the easiest. I'm going to insert a 1 into my function rule and get a -4. I'm going to insert a 2 and get a -1. Notice I'm graphing those points as I go. I'm going to put in a 3 and graph that. I'm going to put in a 4 and graph that. Notice we can begin to see a nice little curve growing here. I went up 1 over 1, up 3 over 1, up 5 over 1, up 7 over 1. I think it's safe to assume that if I were to put in a 5, it's going to go up and over some more. If I put in a 6, it's going to go up and over some more. So there's really no benefit to me graphing any of these numbers over here or plugging those in for my domain. What I don't know is what the graph is going to do over here on the left side. So I'm going to start picking x values that are on the left side. If I put in a -1, notice the rule is take all of x and square it. Since the negative sign is part of x, I'm going to put the whole thing in parentheses and square it. -1 times -1 is 1, minus 5 is -4, and you get this, which you can graph. If I put in a -2, I get -2, -1. If I put in a -3, I get -3, 4. That'll be a little typo there I need to fix. Stick a negative sign on that. And -4 gives me an 11. Now, once you've done this, you can see that a shape begins to form. This shape is a very, very common shape in higher level mathematics, and it always comes about from this particular type of function. We call this a quadratic function, and the curve that's created by a quadratic function is called a parabola. Now, if we wanted to use that as an adjective, we sometimes refer to it as being parabolic. A parabola is parabolic, and it always comes from a quadratic function. And you can see, if I were to take a marker here, you can see what seems to be happening here. On the left, my graph looks as though it's curving down, and this is really hard to do with a mouse, so please bear with me. Yours, I'm sure, is going to look much nicer. It's coming down, and then it reaches this point 0, -5, and it starts to come back up. Again, I'm doing this with a mouse, so please, whoa, that's really bad. Let me try it the other way. And it comes down about like that. That's pretty good. We'll erase those little extra pieces off to the side, just make it look a little nicer. And whoops, there we go. And we'll go back to our pen and we'll fill that in just a little bit. You can see it makes a really nice, neat curve here at the bottom. Now, since this curve seems to be going on forever, I'm going to put an arrow here and an arrow here, and that's what your parabola looks like. Now, it's important for us to realize that the key characteristic for a quadratic, the thing that makes this become a parabola, is this x squared right here. As long as x squared is your highest exponent in your function, you're always going to get a parabola. Now, it is possible that your parabola might be in a different location. Like you could have your parabola over here someplace. Wow, it's hard to draw. You could have it over here someplace and it could be really wide. Or your parabola could be down here and be really skinny. Or your parabola could be over here and maybe be upside down. The point is, every time you have an x squared, you're going to get this basic shape. Now, why is that useful for us? There's a couple reasons for that. Number one, it took us a long time to plot all these points and get this graph. That is the slowest way for us to do this. But if we know what shape it's going to make ahead of time, we can speed that process up. First of all, let me point out to you that if I were to start here and go to the right, this graph is going to go to the right forever, even though it extends off our graph and we run out of room. If I were to start here and go to the left, this graph is going to go to the left forever. That's important because that leads us to our domain. No matter how far I go to the right, no matter what number I pick that's over here to the right, if I stick it into this function, it is going to give me a solution. So if I were to stick in, say, 100, 100 squared is 10,000, take away 5 is 9,995. So the dot out here at 100 would be way, way up here off the graph, but it would exist. It would give me a value. The same is true when I go over to the left. When I go to the left, no matter how far to the left I go, this graph indicates that I will get a solution. So if I were, for example, to take -50 and plug it into my function, well, -50 squared is 2,500 minus 5 is 2,495. So I would go backwards 50 up 2,495 and I'd put a dot. No matter where I go right and left, this will give me an answer. And for that reason, we say the domain is all real numbers. Because no matter what number you pick, along this number line in either direction, it will give you a y value. Or no matter what input you stick in, something will come out. If I look at the range, you'll remember that the range is how this moves up and down. How this graph moves up and down. Well, let's look at what it's doing. Over here, as I go to the left, my graph seems to go up forever. And then if I move to the right, it comes down, 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 down to this point right here. And then it turns around and starts going back up forever. So if I'm thinking about where this graph is going to go up and down, I know it's going to go up forever. But when I look how low it goes, it only goes to this point right here. It only goes down to the point 0, -5. Since my graph goes up forever, but it will never go below -5, I say that my range is any number as long as I pick a number that's greater than or equal to -5. It is impossible, no matter what value I stick in for x, I can never get a -10 to come out. This function does not allow that. No matter what I stick in for x, it's impossible to get a -8 to come out. This function does not allow for that. Everything that comes out of this will be -5 or larger. That's our range. There are a couple other key characteristics I want to make sure I point out in this graph for you. First of all, hopefully you notice that there's a line of symmetry through the middle of our graph. If you remember correctly, a line of symmetry just says that this acts like a mirror, and whatever you have on one side gets duplicated on the other. Whatever you have on one side gets duplicated on the other. Whatever you have on one side gets duplicated on the other. It's called a line of symmetry. Now, this particular line of symmetry happens to be the equation x equals 0. Every vertical line is x equals something. And the reason for that is if you look at the x values along this line, this is the point 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. No matter what x value you pick along here, it's always going to be 0. That's 0, 7. This is 0, 10. The x will always be 0. Why do we care? Well, there's a couple really important reasons. We had to graph, let's see, over here on the left. We had to graph 1, 2, 3, 4, 5, 6, 7, 8, 9 points in order to get this parabola. If I know there's a mirror in the middle and one side has to match the other, then I can look at this and say, oh, as soon as I know this point, I can use the mirror and get the other side without having to plot a point in the table. If I can find this point, I can use the mirror and get the other side without having to plot it in the table. If I can find this point, I find the other side. If I can find this point, I can find the other side. Basically, this allows us to cut our work in half, because if you know one side, you get the other side for free just for knowing there's a mirror or line of symmetry in the middle. Now, the line of symmetry will always pass through the vertex, or the coordinate 0, -5 in this case. The vertex is that point where your graph changes what it's doing. So here it was coming down, getting less and less steep until it reached this point. And then once we had this point, it starts getting more and more steep. Its behavior changes right there. That's the vertex. So if I were to graph this in the future and I wanted to do it much, much faster, I'm going to try and find where that mirror is as quickly as possible. And once I know where that mirror is, I'm going to identify the vertex, or what point lies on that mirror. Then I'm going to work my way up. One side, use the reflection. Next point, use the reflection. Next point, use the reflection. Next point, use the reflection. It's going to make it much, much easier for me to graph in the future. I know that's a lot of information. You're probably going to want to watch that a couple times if it was a little bit difficult for you. I think you'll find as we work our way through these, you're going to find that there are some patterns that you're going to see over and over again. And as you familiarize yourself with these, we're going to be able to do these a whole lot faster than we were able to do them today. As always, thank you so much for taking the time to join us. Make sure you leave us a comment in the comment section. Make sure you like and subscribe and turn on those notifications so you can get all the new resources we have coming out of Nunley Math. As always, I wish you all the very best of luck. Take care of yourselves. Bye-bye.